All right. Good good afternoon, and welcome to this week's Iowa Learning Farms Conservation Webinar. At least for a number of us, it's spring break week, and it certainly feels like spring outside here in Iowa. Unseasonably warm again today. I'm Matt Helmers with Iowa State University and have the great fortune of getting to help moderate a number of the Iowa Learning Farms webinars, and certainly excited for this week's webinar. I think we have a really important topic. Dr. Hanna Poffenbarger from the University of Kentucky is going to talk to us today about winter cover crop effects on the optimum rate of corn across optimum N rate of corn across multiple state field experiments. I can't read today. Dr. Poffenbarger is a graduate of Iowa State University. You got her PhD, I think, in Mike Castellano's lab. So it's great to see the great work she's been doing across the country here, and so now at the University of Kentucky. So with that, the virtual floor is all yours. Hanna, as always, if you have questions, please type those in the chat box and we'll get those to Hanna at the end of her talk. With that, the virtual floor is all yours.
All right. Thank you very much. And yeah, thanks for the opportunity to present today. So I'll be speaking about a project I've been working on for the past few years, a collaborative project across several different states to look at how winter cover crops affect the optimum nitrogen rate of corn. I've got kind of a redundant title slide here just because I wanted to acknowledge off the bat the Precision Sustainable Agriculture team, which is a sustainable ag systems project, larger than what I'm going to present today, but this is one part of it. And there's many different people involved across the U.S. helping with this work, which I'll have on the acknowledgments at the end. But in particular, I wanted to mention Ashmita Rao, Lucas Pechi-Caniceres, and Fernando Miguez, who helped with compiling and analyzing this data set. So I think we all know that nitrogen is an essential and often limiting nutrient for corn. And the vast majority of data sets that we have looking at yield response to nitrogen, we see usually a response. But with that in mind, we also need to consider that fertilizer is not the only source of nitrogen to corn. So this pie chart on the left is data from a review study looking at the contribution of fertilizer and then soil organic matter to nitrogen uptake. So the soil organic matter, as it's decomposing, nitrogen is getting mineralized, converting into ammonium or nitrate that can then be taken up by the crop. And this soil fraction includes not only the kind of the older organic matter that's really part of the soil, but also the crop residues that may be in earlier stages of decomposing that are also mineralizing some nitrogen. So I wanted to mention that just because as we're talking about the cover crops and how they're contributing to nitrogen for the corn crop, they're kind of going to fall into the organic category where that nitrogen is getting mineralized before it's available for uptake. So determining the appropriate or optimum nitrogen rate to apply to corn is challenging in part because the yield response to nitrogen fertilizer is governed by many different processes. So looking in this green box, we can see, overall there's kind of three categories that affect that yield response to nitrogen. How much is coming from the soil, whether through that mineralized nitrogen I mentioned in the previous slide or from any residual fertilizer. The level of crop demand, which is dictated by the crop growth rate and tissue nitrogen concentrations, and then any kind of nitrogen losses, such as denitrification, leaching, volatilization, or even runoff. So there's kind of a lot going on here that can impact how the corn is going to respond to nitrogen. And these processes in turn are impacted by complex interactions of genotype, environment, and management. So which corn hybrid you choose to grow, what the weather conditions are in a particular season, the soil conditions such as texture, organic matter, depth to a root restricting layer, how that fertilizer is applied. So considering like the right source, timing, rate, placement, and then things like planting date. So all of these can kind of combine together to impact, how much mineralization might occur, how big the crop's going to grow in a year, and then what are the likelihood of different loss pathways. And then finally, along with the yield response, we also need to consider economic conditions that can impact the farmer's most profitable nitrogen rate. So if the corn prices are high and the fertilizer prices are low, that's going to favor like a higher nitrogen rate to maximize profitability. Whereas if you have the opposite where fertilizer prices are high, then that most profitable rate will be a bit lower. So because of the challenges with kind of predicting that optimum N rate, or trying to understand all those different factors, one approach to estimating the optimum N rate is just like an empirical approach. So going out into the field and applying different nitrogen rates and seeing the corn yield in response to those treatments. And so that's kind of the approach that we're taking in this study. So using a lot of different site years to get a good estimate of that optimum rate and how it's impacted by cover crop treatments. So with results like this, we can fit a curve. And oftentimes we use like a quadratic plateau function like what's shown here. And with this, we can get some information. So on the left side here, we see where that curve intersects with the y-axis. That's indicating the yield with no nitrogen fertilizer. And that tells us something about the nitrogen supplying capacity of the soil itself and any decomposing residues. We have the slope, which indicates the yield increase per unit of nitrogen input. So that can tell us how efficiently the crop is using the fertilizer that's being applied. And then we have the yield with optimum N, which tells us the yield level when nitrogen is no longer the limiting resource and another resource, maybe water or another nutrient, would then be kind of what limits the yield level. And then we can also estimate that agronomic optimum nitrogen rate, which is the lowest nitrogen rate that maximizes yield. And so it ends up being the join point of the quadratic portion and the plateau. And then we can also estimate that economic optimum N rate, which is the nitrogen rate that meets where this first derivative of the curve equals the nitrogen to corn price ratio, which we set based on the economic conditions, and a common ratio there is 0.1 dollars per pound of nitrogen to dollars per bushel of corn. Now, if you were to do a study like this, like the fertilizer rates, measure the yield, fit the curve, even in the same field, a few years in a row, you would probably find a range of different responses, just depending on the weather conditions. And so you would then have like a few different optimum nitrogen rates. So it can be really challenging to kind of come up with a recommendation, and oftentimes our recommendations are based on an average economic optimum across many different site years. So we can get a pretty good estimate, but in any given year, it might be too low or too high based on the exact conditions in that particular field in that particular year. And this is where cover crops are really important, because you can imagine there are some years where even going with a recommended rate, you might not get very much rain, and then you've basically applied more nitrogen than the crop really needs, and you have some nitrogen left in the soil. So at the end of the season, we have basically what's shown on the left here is these little blue or purple molecules are the nitrate. So that's going to be present in the soil profile, and if there's no cover crop growing, it could leach out in the winter and spring. On the right-hand side, we have some nitrate present, but with the living roots there and the active rye growing, it can take up some of the nitrate that could otherwise leach out of the profile. So we can kind of think of cover crops as a buffer where, we know that it's hard to get super precise with applying just the optimum for a particular field and year. But that if you have a year where there's some excess left there, then the cover crop can help to keep it in the system and keep it from getting into waterways. So cover crops reduce nitrate leaching by about 50%, according to this recent meta-analysis. And so that makes them one of the most effective in-field practices available to improve water quality without taking land out of crop production. And this figure is just, this is from the Practical Farmers of Iowa, showing how with a cover crop you have a greater portion of time with living roots in the soil. And that's really one of the keys to improving the water quality, is having those living roots that can take up some nitrogen that may otherwise be lost from the system. So talk so far about how cover crops can kind of retain nitrogen in the system in the face of uncertainty and in knowing the exact amount of nitrogen to apply to corn. But there's another role that cover crops can play in affecting the nitrogen cycle, which is legume cover crops can add additional nitrogen through biological fixation. And so in a productive legume cover crop, they may contain 50 to 150 pounds of nitrogen per acre, with the majority of that coming from fixation. However, not all of the nitrogen contained in the legume is going to be released and be plant available for the next crop. A general rule of thumb is about, the legume residues are about half as effective in supplying nitrogen to the crop as fertilizer. So the legume is going to mineralize some, but not all of it will be plant available that first year after, the legumes are grown and allowed to decompose. And then finally, legume cover crops typically do not supply enough nitrogen to be the sole source for a high-yielding corn crop. But they may contribute nitrogen credit, so they may help to reduce the amount of fertilizer that would need to be applied. So with that all in mind, we're going to talk about how cover crops can affect the optimum nitrogen rate of corn. And kind of a conceptual basis here is we need to consider two things. So on the left-hand side, this picture is illustrating nitrogen uptake by the cover crop as it's growing. On the right-hand side, this is nitrogen released by the cover crop residue as it's decomposing. So it's important to keep both in mind that if you do have a big cover crop that takes up a lot of nitrogen and the springtime conditions are not conducive to a lot of nitrogen losses, then that cover crop soil may be actually a little depleted in nitrogen relative to the soil that didn't have a cover crop. So that's one thing, that the cover crops have taken up some nitrogen and caused some preemptive nitrogen competition with the next crop. However, if they're able to decompose relatively quickly, a lot of that nitrogen that they had taken up can be released, and a portion of that will be plant available. So these things could counteract each other, and maybe some level of soil nitrogen use, and then if the release equals that, then there may be no net effect on the optimum nitrogen rate. So we kind of need to consider both of these processes in thinking about impacts on the optimum N rate. We can imagine that a cover crop species selection could be really important in terms of both the preemptive nitrogen competition and then also the nitrogen release. So a cover crop like cereal rye, I potted here in terms of like high in nitrogen depletion, because we know cereal rye is a really good nitrogen scavenger, and so it could take a lot of nitrogen from the profile. And if there wasn't a lot of losses, then it may actually decrease the soil nitrogen at the time that the cover crop is terminated relative to a no cover crop situation. And the cereal rye also has a relatively low nitrogen release rate, because cereal rye, at least compared to legumes, tends to have a higher C to N ratio. On the opposite end, we have the legume cover crops, where they're getting a good portion of their nitrogen from the atmosphere, so they may not cause as much depletion. They're not using as much nitrogen from the soil, and since they have a low C to N ratio, they would probably release nitrogen pretty quickly as they're decomposing. And then kind of intermediate is the grass legume mixture. So depending on the composition of that mixture, may behave more like the legume or more like the cereal, but probably going to be kind of intermediate between the two monocultures. So that leads us to our hypothesis that the cereal rye may actually increase the optimum nitrogen rate a bit. A legume cover crop may provide a credit, meaning it reduces that optimum nitrogen rate relative to like a winter fallow. And then the grass legume mixture, we were kind of hypothesizing that may basically lead to no overall change in the optimum N rate, because it's got some attributes of each component in there. Okay, so now this is kind of moving into the experiment and the data that I'm going to present. So the experimental design, we had 11 site years, total of 12, but we're going to focus on 11 because we had one that hadn't reported when I put the analysis together. The sites were managed no-till, and most did not have a history of cover crop use. And this is important because these results are really showing what are the effects of the cover crop on nitrogen supply and optimum N rate in the short term. And the results may be different after long-term cover crop use. We had 4 cover crop treatments: a no cover, which we also call fallow, winter fallow; legume, which was either the hairy vetch or the crimson clover, depending on location; rye legume mixture; and then cereal rye. And then there were 6 different nitrogen rates applied. The nitrogen was applied split, so 40 pounds of nitrogen per acre at planting, and the remainder the V5 to V6 stage. And that was done using urea or UAN, both of those treated with a urease inhibitor. And then all other nutrients we soil tested for, so P and K, and if they were low, then we applied those as well. I wanted to start off by mentioning that we did have some cases that didn't fit the plateau response, quadratic plateau response that I described earlier. So these were excluded from estimating the optimum nitrogen rate. We had 2 cases, Maryland and Nebraska 22, that were linear responses. They never reached the plateau. So that tells us that their optimum N rate was above 320 pounds per acre. So kind of extreme cases. We had 4 site years that had no response. So they may have been limited by another resource. And in certain cases, we can see they were pretty high yielding, and so they may have just had a really high nitrogen mineralization potential, and they just didn't need any additional fertilizer. This figure is summarizing the growth phases for the cover crop and then the corn. So on the left, these left 2 plots here are showing the growth phase for the cover crops. And you can see it's falling generally September to mid-October that the cover crops were planted, and then April to mid-May when the cover crops were terminated. And I wanted to mention too, these are organized from north at the top to south at the bottom. So the northern locations had a bit wider, a longer growth phase for the cover crops than the southern locations. And then on the right, we have the corn planting dates, and those ranged from May to June. The harvest mid-September to December. And here you can kind of see that the planting date shifted a bit earlier, going from north to south. This figure is summarizing the cover crop attributes. So the left-hand side, we see the biomass, the middle is nitrogen content, and the right is the C to N ratio. And then top to bottom, we have the fallow, which is just weeds, legume, mix, and rye. So a pretty wide distribution across the site years for all of these variables. But I did want to highlight that the mixture was generally the most productive in terms of biomass. It took up the most nitrogen. And then it was kind of intermediate in terms of the C to N ratio, with a C to N of 27, whereas that legume had a C to N of 16. So just kind of keeping in mind the threshold level of about 25 is where we see the shift from mineralization to immobilization. So the legume was kind of in the range we'd expect net nitrogen mineralization from the cover crop residue. The mix was like right on the kind of right on the edge, and then the rye was more in the range where we'd expect immobilization to occur. So this figure shows the corn yield response. So corn grain yield on the y-axis, fertilizer nitrogen rate on the x-axis, and then the different plots with the different colors are the 4 winter cover treatments. So this is just showing, all the different site years for the fallow treatment plotted together, and then the quadratic response curve that was fit to those data points. The numbers here are representing the AONR on the left, agronomic optimum, and the right in bold is the economic optimum. So across the 4 treatments, the average economic optimum was 219. But you can see there was a bit of a difference here among the different cover crop treatments. And we'll get into more specifically what's different about these 4 different curves in the next few slides. So in the next few slides, I'm going to show on the right-hand side the yield response to fertilizer nitrogen rate with all 4 treatments plotted together. See that these are the same curves that I just showed, except they're now all in the same plot. And then I'm going to highlight the specific part of the curve that I'm showing on the left side. So in this first figure, we're looking at the yield with 0 nitrogen for those 4 different cover crop treatments. And I mentioned before, this is kind of representing the capacity of the soil and the cover crop residues to mineralize nitrogen in the absence of fertilizer. So we see the fallow and legume had the highest, significantly higher than the mix, which had significantly higher yield than the rye in the absence of fertilizer. So already we're starting to see that the cover crops are impacting the nitrogen supply, with legumes having kind of a neutral effect, and then the mix a little bit of a negative effect, and the rye even a more negative effect in terms of nitrogen supply in the absence of fertilizer. This figure is specifically looking at the optimum nitrogen rates. These are the agronomic optimums, so the yield maximizing rates. And here we can see the fallow and legume had the lower optimums. The mix and the rye had significantly higher optimums. I think the difference here between the fallow and mix was about 25 pounds. And then between the fallow and rye was, I think, 45 pounds. So a slight increase there in terms of that optimum N rate. But definitely less pronounced, at least numerically, for the mix, whereas the rye was the greatest magnitude increase. When we look at the yield with optimum nitrogen, we actually did not find a difference. So this tells us that once the corn had an adequate amount of nitrogen fertilizer, there was no additional or no further negative impact of the cover crops. So it was just a matter of satisfying the nitrogen demand of that corn crop, and then the corn yields were very similar across the 4 treatments. I was also curious, just looking a little bit below the optimum N rate. So if we just chose like 150 pound per acre nitrogen rate, and we didn't attempt to adjust to make sure they were all at the optimum, what the impact would be on yield in that scenario. So yield with 150 pounds per acre as predicted by these curves, we still see a significant yield impact, with the mix and rye having lower yields than the fallow and legume, but that was only a 15 bushel per acre yield difference, whereas with 0 it was more pronounced yield effect of the cover crops. So I'm kind of glossing over a lot of variation by just fitting curves to all the site years combined. So I wanted to show this figure that separates each site year and specifically the cover crop treatments within each site year. Just to highlight that we have a diversity of curves and cover crop effects. So Delaware 21, it's more of a linear shaped response with not much effect to the cover crops. We look at Kentucky 22, and we had a lower optimum nitrogen rate than the Delaware, and a pretty significant cover crop effect. So I was curious why certain site years showed more of a cover crop effect than others. And so that is what we'll explore in the next few slides. What I'm showing in this figure is the difference in the optimum nitrogen rate between the winter fallow and each of the winter cover crop treatments. So where this is positive, that means the cover crop treatment increased the optimum nitrogen rate. So I wanted to tell first if that related at all to how much nitrogen the cover crop had taken up as it was growing. So I plotted that against the cover crop nitrogen content, but really did not see any relationship there. So the next thing I looked at was, again, the change in optimum N rate, but this time in response to the change in inorganic N due to the cover crop. So this kind of relates to the nitrogen depletion concept I mentioned. So where it's positive, that tells you that the cover crop actually increased the soil inorganic N at the time it was terminated relative to the bare fallow. Where it's negative, that tells you like the cover crop decreased the soil inorganic N. Interestingly, we actually found on average like no overall effect, which was kind of going against the conceptual framework I presented earlier, against what I really thought would the cover crop effect would be on the soil inorganic N, but that was interesting. Anyways, there was not any relationship between the change in optimum N rate and the inorganic N change due to the cover crop. And then third, I looked at the change in optimum N rate versus the change in yield with zero nitrogen. In this figure where you see it over here on the right, those are mainly the legumes that increased the yield with zero nitrogen and resulted in a lower optimum nitrogen rate. And then over here on the left, we see the rye and the mixes where they usually decrease the yield with zero N and led to a more positive effect on the optimum N rate. So this was the only explanatory variable that really showed an ability to explain the change in the optimum N rate. So kind of getting into conclusions now, just to return to the hypothesis slide, we can see here that it was supported somewhat. So with that cereal rye, especially a big cereal rye cover crops that we obtained in this study, those led to additional 44 pound per acre for the optimum nitrogen rate. Oh, I meant to change this. This should be pounds per acre because I did convert these numbers. The grass legume mixture plus 24, and then the legume cover crop minus 22. But this one was not significantly different than the fallow treatment. And then so cereal rye inclusive cover crops, they did increase the optimum N rate relative to no cover, but it was interesting to see that at least numerically the effect was a little less pronounced when the rye was mixed with the legume. And also looking at that final figure I presented, just that the yield with zero nitrogen was indicative of impact on the optimum nitrogen rate. So I thought it could be interesting, if you wanted to use like an unfertilized strip following a cover and no cover crop treatments to see how the yield with zero N is impacted in your particular field. That may be informative to tell you whether fertilizer nitrogen adjustments would be needed for using that kind of cover crop. And this is the long list of collaborators who collected the data that I presented. And then there's Lucas and Ashmita, who were postdocs on this project. And that's all that I had. I think the next slide is something that Matt is going to talk about.
Sorry, had to get unmuted. All right, yep, I can handle these. If you watch this webinar live and want to earn a CCA CEU, please email Elena Whitaker, ALENAW, at iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. I'll put that in the chat box, ALENAW at iastate.edu. And please email her with your name, the name you entered to watch the webinar, and your CCA number. And we can go to the next slide.
Oh, sorry.
Oh, no, you're good. You're good. If you watch this webinar live and are willing to fill out a voluntary demographic survey, we'd really appreciate that. Only one survey response is needed for all 2024 webinars. So if you filled one out for 2024, thank you very much. But if not, if you're willing to do so, that would be fabulous. You can scan that QR code or go to iowalearningfarms.org/survey. Again, iowalearningfarms.org/survey. And just to introduce the next webinar, we have Patrick Wall, that's a beef extension specialist. Going to continue on with the cover crop talk. So we got grazing cattle on cover crop. Certainly, I think a timely topic given where we are in the year. And if we have some moisture, I think our cover crops are really going to grow this year. All right, Hannah, we've gotten some questions in here. So let's start off with the first question, we've been experiencing weather extremes. Precipitation shortage can create soil moistures to drop. What are your recommendations for cover crop termination in dry springs to maybe address soil moisture?
Yeah, so we've observed some evidence of that in Kentucky as well, which was kind of shocking to me because we actually do get a lot of rainfall. So I think it is an issue to pay attention to, and it might be the kind of thing where you terminate a little bit on the earlier side so that it's not going to draw as much moisture out of the soil, and then you have a little bit of time for that soil profile to replenish. I would say, a lot of, all the studies that I talked about here were no-till, and having that mulch there on the surface should help to reduce evaporation and retain water. So if you have the option of just allowing, terminating that and then not incorporating it, just allowing the residue to stay on the surface, that may also help when you're kind of trying to conserve moisture. That would be my thought.
Okay, great. Next one, with the urea being applied, was it applied looking at rain event in the forecast?
No, not necessarily. That wasn't part of our protocol. Our approach was to use that. We used something called Anvol, urease inhibitor, so that if it was hot and dry after the application, hopefully that helped to reduce volatilization. And yeah, we hope that the collaborators would kind of be paying attention to the forecast, but it wasn't necessarily part of the protocol to do it under certain weather conditions.
Okay. Would one be able to avoid the higher EONR with a cereal cover crop by being strategic about timing of nitrogen application relative to the corn stage?
That's a good question. And I think there is some evidence to support that timing becomes more important when following a rye cover crop. So there's a study by Dan Quinn, who was a grad student at Kentucky, and he found that with the split application was more beneficial following a rye cover crop. Following no cover crop, it didn't matter as much how the fertilizer was applied, whether it was all at pre-plant or split applied. But following the rye, it was more important to have it synchronized well. And so I would say that if you have the option to do a split application and make sure to get at least some at the time of planting, then that may help to avoid having to apply extra. I'm not sure if that is kind of what the person was kind of getting at, but that's been my observation.
Okay. Next one. When can you expect the immobilized end to become available for plant uptake?
Yeah, well, I'm glad they asked that because digesting these results, I think a lot of the reduction in nitrogen supply with the rye is really due to immobilization more so than that like depletion that I was mentioning or the preemptive nitrogen competition. I think it probably came down to immobilization because it had a pretty high C to N ratio. I think we can think about end immobilization as like a few week period at least, because it's really when that residue is decomposing. The microbes are really actively breaking it down, and they have a high demand for nitrogen, so they're going to take it from the soil solution. But those few weeks, even if it is just a few weeks or even up to 6 weeks, say, it's still a critical time if the corn is starting to enter a phase where it needs a lot of nitrogen. So I don't have the exact numbers, but I would guess sometime around July that probably the end immobilization would switch to mineralization, but it may be a bit too late if the corn has already had entered that phase where it has that high demand for nitrogen.
Next question. Why do you think the legume grass mix had the highest N content compared to the legume or rye alone?
So I think, and there's been some other studies that have like documented that the mixture can kind of merge the benefits of both, and you can even get some synergisms where if you're just growing rye by itself, it's only getting its nitrogen from the soil, and it's kind of going to be limited by whatever nitrogen is present in the soil. If you have a legume too, then that legume can kind of fill a different niche. It's able to get its nitrogen from a different source. And so you may get as much soil nitrogen uptake by the rye in mixture as you would in monoculture, but then you actually have an additional amount of nitrogen that is coming through the legume from the fixation. So I guess in my mind, it's kind of adding together two different sources. The legume by itself, they usually grow smaller than the rye, so they're probably not taking full advantage of what nitrogen the soil could supply. So yeah, adding them together, you kind of get the full soil nitrogen scavenging by the rye, and then the nitrogen fixation component to give you an overall greater nitrogen uptake by the cover crop.
Okay. Couple questions here. Do you think the EONR will come down for the rye sites after multiple years of cover crops? Thinking that some of these may be new to cover crops.
Yeah, I definitely think that that's a kind of a weakness of this study is just that we were only focused on the short term, and if the cover crop is building up the soil organic matter, then it should be increasing the ability of the soil to mineralize nitrogen over time. And it definitely makes sense in my mind that after maybe 5 or 10 years of using a cover crop, you have a system that can mineralize nitrogen better, and so you might not need this increased EONR at that point.
All right. Okay. Somebody said great talk. I would agree. Was there a differing response to cover crop mixtures for sites with high or low soil organic matter?
This is a good question, and there's so much to explore. I haven't looked at that yet.
Okay.
That's definitely on the list of something to plot and try to analyze that. But no, I can't answer that right now.
Okay. Um, this person indicated in one of the slides, it looked like the yield in the Nebraska trial seemed quite high. Was that field or were any of the fields irrigated?
Oh, yes. That's a good point. I forgot to mention. I know Delaware was. So Delaware was a sandy site and they did irrigate. And I am fairly certain that Nebraska was a rain-fed site, but I could be off on that. It is possible that in certain years they did use irrigation. So I can't answer that 100%. But those would be the only two.
It did look
Delaware
like
and
the
Nebraska.
Nebraska site was more in eastern Nebraska, if I remember that correctly.
Yeah. I want to say, they said it was not irrigated.
Okay.
Yeah, you're right. It's on the
Looks like it
eastern
might have been,
side.
yeah, it might be near Lincoln.
Hmm.
So, all right. I think those answer oh, no, there was one. Was there a cover crop termination by site or termination height by site or for all the sites consistently?
No,
Okay.
we basically advised for each location to try to allow that legume to grow as much as they could, and the guidance that we gave was to aim for 2 weeks prior to corn planting, but it's always kind of hard to predict exactly when corn planting is going to be. So I'm sure it wasn't always just 2 weeks before. But I will say that we kind of saw that the northern locations allow their cover crops to grow longer than the southern locations. So I think that did kind of even out the fact slightly, the fact that the northern locations probably, their environment isn't as conducive to growing big cover crops as the south. So I don't think that they were all at the exact same growth stage, but that was the goal was to try to do 2 weeks before planting and allow the legume to hopefully at least get somewhat close to flowering.
Okay. What was the crop before the cover crop was planted? Was it, I guess, consistently corn or soybeans or?
We had a diversity of that
Okay.
too. We wanted to try to get the cover crops in for the optimum planting window for the legumes. So most sites planted the cover crops after either silage corn or a small grain.
Okay.
But we did have a few sites that planted them after corn or soybean, like grain harvest.
Okay.
But most tried to have like an earlier harvested crop so they could get the cover crops established earlier in the fall.
Okay. All right. Now I do think we have reached pretty much all our questions. So again, if you need a CCA CEU, please email Elena Whitaker, ALENAW at iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. Please tune in or let folks that might have interest tune in next week for Patrick Wall talking about grazing covers. And with that, Hannah, I want to thank you very much for being willing to present and sharing this important work. I'll give you the last word.
Oh, yeah, thank you so much for the opportunity, and I enjoyed it, and I really enjoyed all the questions. So thank you very much.
All right. Everybody have a great rest of the week.